Hello, everybody, and welcome to episode 71 of the Hyperthesis podcast. This is the first episode of our 6th season, and we're joined by a very special guest today, Wyatt Kirkby. I'm Liam.
I'm Feely.
I'm Patrick.
And Wyatt already said hello. I messed up. I messed up the introduction, but that's okay. We're rusty. It's been a little while since we recorded. So our special guest Wyatt. So Wyatt is a physicist studying quantum many-body systems with a focus on exotic phases of matter and their dynamics. He's originally from Ontario and moved to the east coast of Canada to pursue a degree in jazz performance at St. Francis Xavier University. So we all went to the same university here, but Wyatt, you were a few years ahead of us. So I think when we arrived, you had 1 year left or something like that. But so we've met before, which is why you're here. But after deciding that jazz was not something you wanted to pursue professionally, which we'll ask you about later, I'm sure, Wyatt switched to the physics program and completed his undergraduate honors thesis under the supervision of Dr. Brandon Van Zyl, where he studied density functional theory in two-dimensional dipolar gases. After Wyatt completed his Bachelor of Science in 2015, he moved to McMaster University in Hamilton, where he completed his Master's of Science in 2017 and his PhD in 2022 under the supervision of Dr. Duncan Odell, which is my current supervisor. So we'll probably talk about that again, how that happened. But anyway, so afterwards, Wyatt, he moved to Innsbruck, Austria for 1.5-ish years to work as a postdoc in the group of Russell Bisset, I said that correctly, and he's currently doing his second postdoc at the University of Heidelberg, co-supervised by Lorraine Comaz and Thomas Gazenzer. I might have butchered those names. I apologize. You can tell me if I was wrong.
Yeah, it's you got Russell's name right. Lorian Comaz.
Oh, okay.
And Thomas Gazenzer.
Okay. Sorry about that. I apologize deeply to them.
All right.
Welcome, Wyatt. It's great to have you.
Nice to be here. I graduated in 2015 from St. FX, so I don't know what year.
That was the year we started.
We got there.
Yeah,
there was no overlap.
Okay.
I thought there was 1 year of overlap, but maybe I just have a wrong memory.
I think I just kept coming back.
Yeah. Oh, yeah. You came and gave some talks, I think.
Yeah.
And I think we heard about you from the profs a lot.
Yeah, maybe.
But we did work for the same guy, so I think,
Yeah.
Yeah, that 1 year me and Feely worked for Brandon. I think we saw your name in a lot of papers. But before we start asking you about your life and your research a bit more, I have an intro topic that I wanted to discuss about the phenomenon of second sound, which I admittedly know way less about than I should, but that's because I haven't had to deal with it in my research yet, so that's my excuse. Oh yes, so I found this paper that was recently published in the Journal of Science on February 9th, 2024, titled Thermography of the Superfluid Transition in a Strongly Interacting Fermi Gas. And they claim to be the first paper or the first group of researchers to take an image of the existence of second sound, which is a special type of wave that transfers heat. You can think of it like that. So typically when something gets heated up, the heat spreads outwards from a localized source and it eventually dissipates. So for example, if I'm in my kitchen and I turn my oven on and I open the oven door and I just leave it on like that, the whole kitchen will eventually heat up because the heat transfer from the elements will transfer through the air via diffusion. And if you're closer to the oven, it'll probably be warmer. And if you're further away, it'll be a little bit colder. However, for very, very cold systems like these Bose-Einstein condensates and superfluid helium, which are things we've talked about a whole bunch before, and I think kind of recently with superfluid helium, actually, although I don't remember. But anyway, for really, really cold fluids like these Bose-Einstein condensates and superfluid helium, and certain types of solid state systems, maybe, although that last one I'm not 100% sure about. Quantum mechanical effects can manifest in these systems, and heat transfer can occur in a different way as well, opposed to the usual way. So in solid state systems, at least the ones I'm familiar with, you can transfer, or fluid mechanical systems, heat can transfer by sound waves, which is the motion of the fluid.
Well, it kind of makes sense, right? Sound is the mechanical wave, and mechanical wave is like motion of its medium. And some people would think, kinetic energy in the motion is like considered similar to like heat and temperature. And so it makes sense in a way you can heat something up by putting sound wave through a lot. Like if you have like really high amplitude sound wave, so it's like make things move and hopefully create some heat. Or even, would you consider that heat in itself?
Would you consider the sound heat or the energy, or what?
Isn't heat just kinetic energy?
Yeah. I think there's a lot of different descriptions of heat, I guess.
Yeah. Classically, maybe.
I mean, so admittedly, I don't know actually nearly as much about second sound as I should either. But okay, so my understanding comes from the fact that when you have something like a BEC, there's one way of looking at it that I think was one of the original ways of looking at it, which was there's this so-called two fluid hydrodynamic picture, where you take your BEC and you divide it into a kind of a normal fluid, which is thermal and not superfluid, and then you have the superfluid piece. And if you have, I guess, two fluids, then you have two sounds, but it's in some way the sound is mixed. It's not like the speed of sound in one and speed of sound in the other. And then they describe this second sound as a sort of entropy wave, which is a bit weird. A bit of weird description, but I guess the point is that it's the nice thing about it is that it's a measure of the superfluid fraction of your condensate or whatever. So if you have you can use the speed of second sound to determine how much of your condensate is actually condensed. And so it's if you have a high superfluid density, then I think you end up having a really high high second sound, and then vice versa.
Yeah, I always get a little bit confused about the difference between like the regular sound and the second sound, because like in these really cold systems where these quantum mechanical things can happen, you can transfer heat by sound waves, usually like the normal fluid component sound waves, which in a quantum material, they're these little packets called phonons, right? So they're like your particle of sound, which we've talked about before a lot. And they're kind of fluctuations in the displacement and density of the particles, like the atoms or molecules. But then you have this second sound, which is the heat and temperature can transfer from this like wave-like motion. This, I think you said it was like an entropy wave. I read through some literature and people call it like a temperature wave or something like that. So I guess its first sound is a pure density modulation, while second sound is a variation in the density of excitations with no variation in the total particle density. That's right. Which is, I kind of paraphrase that from a paper I found. So I guess in other words, like it's a pure temperature wave with transferred heat, because it's not an actual like mechanical change in density.
Mm-hmm.
So it's weird. It's this weird thing, and it's like standard ultra cold atomic gas theory. You see it everywhere in these textbooks, but I just haven't really dealt with it yet. So I'd like all the Bose-Einstein condensate calculations I've done, I just look at like I think your regular phonons. I've never thought about second sound, so I don't know why you can do that or why you can ignore it sometimes. And
well, I mean, the truth is you have to. It only really exists at like a lot of the. I guess it depends what you're doing, but for example, if you're doing stuff with the theory with the Gross-Pitevsky equation or something like that, you're thinking of it at zero temperature, and so there's nothing to think about in terms of there's no normal fluid left, right? So you can't have two sounds, you only have one sound.
Oh, I see. I see. So your phonons in like a t equals 0 BEC are they second sound phonons then? Because there's no first
Well,
one.
it's not. They're not supposed to be heat at 0, right?
Yeah,
Yeah.
it's an isolated system with no
Oh,
feedback to some bath or anything like that. So you can't have two
temperature.
sounds in that sense. Um,
So you can only have the regular density modulations there, I guess.
yeah. Okay, but I say this, but there are ways of getting other sounds, but it's yeah. There's it. We can talk about that later. In a super solid, you can have two sounds, for example. But
Yeah. So we talked about super solids in our last episode, I think, actually.
oh,
Because I was talking to you a little bit and looking at some of the papers you published recently. And I even saw like a paper. I didn't read it, but it was like talking about fourth sound, which I guess implies there's a third sound. So like, what are third and fourth sounds? Is there a fifth sound? I don't know.
I feel like this is like one of your regime because once you get below like to ultra cold stuff, my knowledge is like also drops like the temperature, like the heat. As I don't know that much about the ultra cold system. I know there's a lot of quantum mechanics there, but I think there's something weird happen when you get like really cold, and also like I think I deal with a lot like 0 temperature in theory, um, but it doesn't exist. I mean, in experiments yet. Like we haven't achieved that, or I don't know if we will. But so I don't know what really is gonna happen there apart from the theory.
Even the stuff I do, it's all like 0 temperature. And you can put in like small temperature corrections. Feely, even that paper we just did with Dean on the dipolar Fermi gas, that's a 0 temperature thing. You
Yeah,
can
and you
kind
add some perturbation to it, right? Like,
yeah.
yeah, to make it like small temperature.
But kind of just to wrap this topic up, so the second sound, it's this weird kind of thing. We've known about it since 1941, thanks to Lev Landau, of course. But so back to this paper I mentioned. We've known about it for a long time, and we've even been able to like experimentally kind of, I don't want to say prove it since the 50s or 60s, where it was first seen in superfluid helium through some experiments. But until now, no one's actually been able to take a picture of it. So it's like black holes, which we've talked about before, where we've known black holes have existed for a long time. You can see their effects in space. You can see their gravitational lensing, but only in the last few years were we able to take like an actual photo of one with a bunch of radio telescopes. It's that big orange blurry blob image that you might have seen floating around. It's the same thing with second sound. So this paper, they were actually interestingly enough, they were actually able to use radio signals to take a photo of it, because taking a photo of an ultra cold fluid can be difficult because they're so cold they don't emit the usual infrared radiation that people are used to imaging. So what they had to do was they took a strongly interacting atomic Fermi gas. They didn't actually use a Bose-Einstein condensate, and this Fermi gas emitted radio waves such that the warmer the temperature, the higher the frequency of the radio waves it emitted. So by measuring the emitted radio waves, they directly observed that once they took this ultra cold Fermi gas, they dropped it below some critical temperature. They witnessed a phase transition, and they directly observed this sudden change from thermal diffusion of heat to second sound wave propagation of heat. So they're actually able to see like this second sound wave sloshing back and forth within their kind of container. So imagine you have like a bucket of water and you make a wave in it, it bounces around. They kind of got something like that, but with this second sound. That's my kind of naive understanding after going through their paper a little bit. And although I have no proof to back this up, they claim that it has applications in creating high temperature superconductors, and that you can actually use it to help understand the physics on the inside of neutron stars. So that's kind of interesting.
I mean, it's pretty neat. I mean, I actually didn't see this paper, which is a shame because I probably should read it. Although I see it's on a Fermi gas, I guess, in the I suppose in the BEC phase, which is interesting. But to something you mentioned before, yeah. So there's first sound and there's second sound, and there is fourth sound as well, which has been hypothesized for helium. I think it's in helium in capillary. if you put helium in flowing in a capillary, I'm not sure how to say that word.
Me either.
Apparently you can get fourth sound there, which I actually only recently found out about as well. But I've never seen anyone talk about something called third sound, and I've always wondered this: like, is there a third sound, or did we just jump from 2 to 4? I also didn't realize that no one had observed it before, because it's in the textbooks, right? So this is new to me. So
Yeah, like-
thank you for bringing it to my attention. Actually,
Well, like they've observed it, and like I found a good YouTube video of this guy in like the 60s explaining some experiment that detects it. So they've detected it, but they like never like photographed it, I guess. They never.
I see.
I think that's what they were trying to do. And their paper claims they're the first to do it, which
Yeah.
I trust because it was published. It probably went through peer review. But
Yeah, I actually know. Okay, so I know Chris Vail, who's kind of one of the middle authors. He's
oh, okay.
experimentalist from Australia, I think originally. Yeah, Melbourne. There you go.
Mhm.
And I'll actually be meeting Martin Zwerlin, the kind of head here, in 2 weeks, I suppose. He's coming to Germany, and they'll be coming to Heidelberg. So maybe I'll ask him some questions about this.
Yeah, let us know. I've seen his name floating around.
Yeah,
every
he's
now and then.
definitely a big wave.
Yeah, academic world's kind of small too. I remember talking to my supervisor, like the list of names I was gonna see. People are gonna see at a conference. Like, oh, I know this person. I know this person. I met this person. It's like I never heard these names before in my life.
Yeah, I guess when you've been in it, the longer you're in it, the more people you meet, right? But yeah, I've always seen second sound floating around in these Bose-Einstein condensate textbooks, and I figured now was the time to read up on it a bit. That was my intro topic. So now it's on to you, Wyatt. We're going to ask you some questions about yourself and your research. So, what do you do? We'll start with that.
Okay, yeah, good question.
Yeah.
So, I'm a theorist, so and I work pretty closely. So Lorianne, one of my supervisors, she is building a lab here, so it's still in the building phase, and it's for ultra cold atoms, specifically highly magnetic ultra cold atoms. So there's two. Well, okay, there's a few highly magnetic systems that have been condensed. The first one was chromium, and then was erbium, and then dysprosium. I'm not sure about the order of those last two, which one is first, but I'm pretty sure that's right. Anyway, so they're building one with dysprosium, which is the most magnetic atom on the periodic table, tied with holmium, but holmium has not been condensed, so we don't have that option right now. And so I'm a theorist, and my job, part of my job, is to kind of simulate what they do in the lab. So they'll say, okay, we've got this sort of trap with maybe they say, okay, we've got this temperature and this many atoms. What can we see, and what can we do with that? And so I will simulate some of that when I'm working with the lab, and then when I'm working with, say, closer to the kind of pure theory side, is more with what Thomas is doing, and we're kind of looking at dynamics and stuff like this, still within the dipolar quantum gas world. So, but maybe a little less direct applicability to experiments. So, much larger systems and just simulating stuff that could happen in the future, maybe with experiments.
So would you say your work is more on the analytical side or more like a numerical side when you say simulate? Like, is it more like solving big equations, or it's more like numerical model?
It's probably 70-30 simulations right now. Yeah, so a lot of the stuff I do, I don't know if you've talked about this on the podcast before, but the Gross-Pitevsky equation is like the kind of the main workhorse of ultra cold atoms, especially BECs. And then I play around with that, but in its various forms. So to get into the nitty gritty details, sometimes you need to add extra terms, sometimes you need to add temperature in different ways. and so a lot of it is simulating the Gross-Pitevsky equation in its different forms. But then also there's some analytics that go along
But
with
so
it.
it's not like a molecular dynamics kind of type, because I think that was what I'm more used to, like Monte Carlo, MD, and those stuff. They don't do that in ultra cold systems, do they?
So they do, but the problem with something like Monte Carlo is so there's actually quite a bit of a lot of ways you can do it. Monte Carlo is one of the ways, but the thing is with Monte Carlo, right now is you're kind of stuck with on the order of hundreds of atoms, and it's you can get some really good stuff that way, and there's people they're really pushing for to get larger and larger systems, and I would say that we talk a lot with those people as well, and there's actually some maybe competition with those people as well, but kind of Monte Carlo is not enough. You can't use it to do the size of systems we're talking tens of thousands of particles, which is simply too big. There's another way that we're kind of looking at treating these systems exactly. It's called the complex Langevin, which is like a stochastic approach to solving the exact path integral.
It's like Langevin dynamics stuff.
Yeah, it's you solve sets of stochastic equations, and then you
like Brownian motion kind of type.
Yeah, exactly, yeah, that kind of thing. It's basically taking that in a very like complexified way, and you can get some ground states that way exactly for large system sizes, but it has its own kind of limitations as well.
Yeah, the Gross-Pitevsky equation, for people who might not know, you're taking all these bosons that are interacting in whatever way, and you're doing this mean field thing. So you're saying, when they're really cold, most of them occupy the same state. So the state's like, what is its we've talked about this before. I don't want to spend all day talking about what is the state, but all the particles are kind of behaving the same way when it gets really cold. So you can approximate the physics of it to this one equation, this Gross-Pitevsky equation. But that equation, because you've approximated things, I think it becomes nonlinear. It's this nonlinear equation, which means it's not easy to deal with. And yeah, like Wyatt said, you can put extra terms on it. If you're studying dipolar boson sign condensate, like Wyatt is, you get this extra long range interaction. So not only do the atoms bump into each other when they get close to each other, when they're far away, they act like little magnets and they kind of repel or attract each other, depending. So it can get really complicated. And so yeah, like if you're trying to do exact simulations, like maybe these Monte Carlo simulations are trying to do, it can get messy, and having just one equation for it is kind of nice. It's easier to do a lot of the time, I think.
That's one thing I love about talking in theory, is that we see 100 or like 10,000 particle as large, where in real life a few grams of a material contains like 10 to the 24 numbers of molecules or atoms, right? And then that's like, we are not anywhere near that. But somehow when you go to that many particles, the description is, you can use macroscopic description or kind of a statistical description for a lot of things, where it's interesting, but you don't get that what's going on in, let's say, in the small scale level, right? That's why we like to study is like only like few hundreds or a few 10,000 particles. I don't know what's like, is it really feasible to computationally do like 1 mole of material? That's too much.
Yeah, so I know that like what's a bit funny is okay, ever since the first BEC, okay, they didn't have that many particles, let's say, but let's say in the past, I don't know, 10 years or so, getting something like sodium, which is a well understood just contact interacting gas, so close range acting gas to condense, you can get on the order of millions of particles, which again is still not even close to macroscopic, but
slightly better.
But yeah, slightly better. But with these like highly magnetic systems, it's a struggle to get anything above, like getting 100,000 would be a significant achievement. And that's just all due to the strange interactions that come with these little magnets, the particles acting like magnets. There's all kinds of weird behavior, and but getting something on the order of a mole would be a dream, I guess.
I mean, I heard about like 100 million particles for molecular dynamics stuff, but that's not even near a mole.
Yeah. I guess it must. So the things you're studying, these highly magnetic particles that you want to make into a BEC, because I think the way it works with maybe sodium, like the more basic ones with just contact interactions, you got to cool these gases down. And I think the way they do it is they use this kind of magnetic evaporative cooling thing, and then they laser cool it, and then you get them really cold, and they only exist for a little while before they crystallize, but it's long enough. So how do you even cool down these magnetic particles?
Yeah, that's a good question. So actually, usually I think the evaporative step is the last step.
Okay, I got it backwards then.
But I think that was actually the key to getting the BEC. Was basically evaporative cooling was invented. But yeah, so there's a few different ways. The very kind of standard way is, okay, so what you do is funny. You actually, the first thing you need to do, because a lot of these things, it's like we're talking, sodium, we're talking dysprosium, we're talking lithium, rubidium. All these things are metals, right? So it comes to your lab and you've got a chunk of metal. and then what you need to do is you need to heat it up really hot so that it evaporates. And then very typically what happens is you shoot it down, it heats up and you shoot it down a tube, let's say, and a lot of them get lost, but some of them make their way down this tube, and then you've got this thing called the Zeeman slower, which basically uses magnetic fields to slow down the atoms using the Zeeman effect, which maybe the listeners know about, maybe they don't. I don't know, but
probably not. But
you use like the atomic transitions in the atoms to cool it down in a combination with laser cooling. It seems weird. Lasers seem to, you would think, oh, lasers heat things up, but actually you can cool things down because light has momentum and it can push back on the fast flowing atoms. And then usually you trap them in what's called, so at the end of this Zeeman slower, you have this thing that you is for atoms, for neutral atoms, you have this thing called a MOT, a magneto-optical trap. And it's just a bunch of lasers and a magnetic field, and they're all kind of pointing in different directions or multiple directions. And it's basically just using the atomic transitions to push the atoms back into the same spot. And then at some point you do this evaporative cooling where you have a bunch of atoms which are stuck somewhere in say like a, you can picture it like a bowl where you just like let the edges of the bowl get a little lower so that all the hot atoms pop out. And then on average, even though you're losing particles, your gas is actually getting cooler that way. And so it's a combination. It's a very difficult thing to do, and then how you actually do it depends on the lab itself. This lab that I'm in now doesn't actually use the Zeeman slower. It uses a second magneto-optical trap just to trap the atoms quickly. But I don't know why they chose to do that. They just did. But it's a process. It's a difficult process, and it takes years of work.
Do you know how they prevent crystallization?
You can't prevent it. It happens eventually, I think, no matter what, because of three body interactions and things.
So you kind of have to do it quickly and get your data quickly then.
Yeah, for sure. A lot of these things are only surviving at most on the order of seconds, and very typically on the order of milliseconds. So they will combine, they'll form molecules. You do change. So you have to remember that these are not necessarily your standard energy levels in atoms, right? Because you're using magnetic fields to play around with the energy levels, and so they're not behaving necessarily the way you would expect them in like just put them together and get chemistry out of or whatever. But yeah, sometimes you can play with the magnetic field, for example, to tell them whether or not you want them to bind with each other strongly or not. And that's how you can actually control the interactions between particles. But in the end, they are going to recombine, and in that way, once they become molecules or something like that, they're just going to fall out of the trap, and then you just lose atoms.
This sounds like a very extreme version of supercooled system where you want to study this really fast metastable state, but you can only keep that for very short time. I think even similar people who study water, I think Peter Poole would know more about it, right? Like when this really specific condition is really hard to get. You can get it, but maybe for milliseconds or something. And if you get a second, that's very long.
But like on the scale of atomic physics, like seconds are very, very long. Maybe on our
Yes.
time scale it's short, but getting a BEC for a few seconds, that's pretty long as far as a BEC is concerned.
Yeah, I guess for if you use something to probe it, maybe light and stuff, like the wavelength and like the frequency is really short. So you actually, if you think of how many times that pulse can hit, I think that should be a lot in a second.
Yeah, if you have something for a second, even though on a human scale that's really fast, from their perspective, it's a lifetime. You can do a lot of physics there, which is nice. But yeah, they're down at the order of, very typically these systems, cold atomic systems, can get to even 20 or even 10 nanokelvin, which is crazy.
Yeah, the systems
Cold.
the systems I'm doing theory for, they created them in the nano, like I think it was like 2 nano, was it 2? I feel like it was 2 or 20 nanokelvin, probably 20, but
Yeah,
that's really,
it can be very, very cold.
yeah. But for the sake of time, I think we should, so that's kind of what you're doing now with these highly magnetic BECs. Feely is one last thing, I think.
Well, this is kind of moving on stuff, but since I think you're the first postdoc in our on a podcast, I want to ask, like, if so is your day-to-day much different from when you're like a senior PhD student or even like a graduate student in general?
That's a good question. I feel like I mean, it changed with the PhD. At the beginning of the PhD, I felt a lot more like a student because I was taking classes and didn't really know what I was doing. I mean, I still don't know what I'm doing, but it's different, I guess. Right now, I think there's a lot more. It might be more different internally in that I treat it more like a job that I do, during the day, like a 9 to 5, even though, okay, maybe I'm not always in at 9. But I try to separate it a bit. Whereas I think a PhD, it kind of is your life for a while. So the project needs to get done, and you're just doing the project until it gets done, right? So I would say I like it. I like in that that separation, in that I feel like I have a lot more of a work life versus a home life now. But when I walk in, I just try to do the research and what I can do. I don't have to. I'm not doing any teaching, for example, so that gives me more time for research. I liked some of the teaching that I was doing before, so it's not necessarily a good or a bad thing, but a little different.
So we worked for the same, well, we ended up kind of taking the same path by accident. So we all went to the same undergraduate university, and then you went and worked for Duncan, and I kind of accidentally stumbled upon him, not knowing you were working for him somehow, but then finding out quickly that you worked for him. And I'm like, oh, Wyatt, I've met Wyatt before. So how did you end up kind of like working for Duncan? And can you talk to us a little bit about what you did working for him? I mean, I know what you did, but people listening might not.
Yeah, so actually after leaving well, okay, I was getting ready to leave to graduate from undergrad, and I did a tour of a bunch of different universities. I went to McGill, I went to Ottawa, Carleton, and I went to McMaster. And actually, at McMaster, I was slotted to meet with Jules Carbot, who is an emeritus at the time. He's since passed away, but he was like an absolute kind of powerhouse in
Yeah.
the superconducting community. And he was at McMaster for a long time, and he was still taking on students as an emeritus. And I talked to him and had a very nice conversation. And at some point, because McMaster, the way they do it is they got you to meet with a whole bunch of people. I got to talking with Duncan at some point, and he showed me his coffee cup stuff, and he said, "Oh, well, I'm looking to have a co-supervised position with another high energy prof, and that's something that you could do." And I thought about it and said, yeah, sure, that sounds great. And then actually, when I got there, the high energy prof had left, and so it was just me and Duncan working together. So it was a bit luck based, just that. But in the end, so I ended up working on the stuff he was really interested in, which was caustics, and this catastrophes and all this stuff in dynamics of quantum systems. Perhaps you've probably talked about caustics before.
I gotta say, your group got my friend here addicted to rainbows and all these stuff. He always like, oh my god, this is this type of rainbow. I see this today. Here's the picture, and like, dude is like obsessed with caustics.
That's me. That's me now. Like, even though like your regular rainbow is a caustic, and most of these other types of rainbows aren't, I'm still like obsessed with all of them now.
I'm pretty sure for the first 2 seasons of this podcast, there was not an episode where caustics were not mentioned in some form or another. And even now it's, if not every episode, at least every second episode.
Yeah, like
you see any asymptotic divergence, you're like, oh my god. Or
well,
it's tradition.
Our cover photo is the Piercy function, so like, which is it's the cusp caustic you see inside your coffee mug when you zoom in close enough, and
yeah.
So
yeah,
you were doing like quantum catastrophe theory, Duncan likes to call it.
Yeah, we were basically doing what I guess, to put it bluntly, it was what Barry did in the 70s, but with quantum theory instead of light, and maybe with a little less rigor, say, than John Nye, who absolutely did everything to do with light and caustics and everything. But there was quite a bit with that, and I also dabbled a little bit with stuff I really found interesting was a little bit of this. What happens if you introduce? What's the difference between an integrable system and a chaotic system, and how does that affect caustics? And how do some things about integrability and thermalization, and how do systems thermalize, and random matrix theory got in at some point. I thought it was all very interesting. So,
to move on a little bit, actually, this question probably be useful to us a lot. Is that what is it like? Like applying for postdoc position. Like when did you start thinking about it or applying? Like, because I think most of us are going to our more like senior years of our PhDs, and I think like I don't have that much of an idea what the process would be like. I always think that I will cross that bridge when I get there and talk to my supervisor and stuff. But I want to hear like what's your story when you like close to finish your PhD?
Yeah. So so I was in the same sort of boat. I didn't know what to do. I asked a former group member, Ryan, who was with Duncan as well, and he actually applied to, I think, 120 postdoc positions.
Ooh.
It was crazy. I didn't do that. I initially I just grabbed a bunch of names whose research papers I read and stuff was like, I like this a lot. I just sent them emails, and I got 0 responses. I only sent like 6. I don't know. I didn't get any responses, and then it was COVID, right? So I basically was in a position where I was like, okay, I can stay a little longer, and everything's shut down, so I'm not going anywhere. And I just kind of waited a while until basically I was searching every day for what positions are open. I would send out applications. I started to hear a few responses, nothing too crazy, but then I just randomly found this posting for a job in Innsbruck and I applied. And yeah, so I would say that if you want to look for postdoc positions, you should keep your eye keep your eye on some of these job boards that exist and just look every day. Maybe don't do the 120 applications, but just
So you were looking like international, like globally, right? Or you more like focused like in Canada, or if it just like doesn't matter. It's more about the work.
I was looking globally, but I probably admittedly would have had my limits. Like I applied to, for example, OIST, the Okinawa Institute of Science and Technology, which would have taken me like about as far as you can go. And I mean, that place is amazing. If you ever get a chance to visit, definitely go visit. I didn't get the position, but there's a lot of jobs. There's a ton of jobs in a lot of places, but you also should consider, like, yeah, do you want to live at this place for a long time? And postdoc's nice. I mean, it's only maybe, it's not a commitment forever, right? So you could just say, hey, I want to be somewhere new for 2 years, 3 years, whatever. And so when Austria came up, I said, sure, why not? And I got the job. So
Yeah, so I think we have to think about those things. And people keep asking, what are you, what are you gonna do after your PhD? I was like, well, don't ask, don't tell. I have no idea. So, but I've got to walk you back down memory lane a little bit. So I heard you started an undergrad with jazz, which is I think quite far from physics.
Oh, careful.
um,
Music is
well,
just applied physics, right?
yeah, but you don't see a lot of music students who went into physics, right? And you hear more like mathematicians who become physicists or engineers who become physicists. But I actually never heard of like even Catherine, who was on our podcast. She was in history, and I think that's pretty far too, right? And then she came into physics, and
Peter Marsland.
yeah, Peter Martin plays classical guitar,
But
right?
he-
But I
he
think
was- He was gonna do music. It was between music or
Yeah.
physics, and he chose. So you and Peter
Yeah, but
Marsland are similar, Wyatt.
it's not common, right? So what was that? What was that journey? Can you tell us about that?
yeah, I mean, that journey starts in high school. I mean, I was always good at math, and I liked music a lot. And in a lot of ways, math and music are intimately connected. I think jazz is a bit funny because it's in some ways it has no rules, but in other ways it's so complicated and it has so many rules. And yeah, I just didn't know what to do in leaving high school. So when I was looking to apply to university, I had a bunch of applications and I asked a lot of the big schools like U of T, McGill, UBC, in Canada at least. I asked them, hey, can I do both? And they basically all said, no, you cannot be in both departments at once. But at the smaller school, they were like, okay, you can try. And so then I thought the easiest thing to do was to go in as a music student and take a physics course on the side, which I did, because in first year you only needed to take physics. You also needed math, but it was first year of physics, so I thought figured I could do it, and it went well. But then actually, I decided that I couldn't. I became actually kind of a little disillusioned with practicing all the time, and it was way more competitive than I was expecting, and it made you really, me personally, actually kind of it became frustrating to compete with your fellow student for like for something that was supposed to be really joyful, this music. And so I thought, you know what, I'm going to do physics instead. I was convinced. So yeah.
Yeah, you get these musicians who practice like 8 hours a day kind of thing, and you're just like,
yeah, you spend 6 hours, 8 hours in a gray room just practicing all day, and you're like, this stops being enjoyable after a little while, right?
So when you say jazz, one of my roommates in undergrad, he was all in jazz, but he was a singer. Were you a
Yeah.
singer or were you like more like instrument person?
No, I was an instrument person. I played the saxophone.
Oh, nice.
Which one? Or all of them?
If you could play one, you can play them all, but mostly tenor was the one I stuck to.
Okay.
Right, Liam, like bagpipe, you play one, you play them all. You even play the flaming one, right?
I can play the regular bagpipes, and I can
what's
play
called the elbow pipe.
the small pipes. But then there's like 100 subdivisions of the small pipes, and so I don't. There's some of them I can't play. Like there's Irish ones that are just way too complicated for me.
Oh, maybe they made it so the Scottish people can't play.
Yeah, probably. So yeah, you finished your. You swapped over to physics and you liked it, and you did some density functional theory, but maybe for the sake of time, we shouldn't get into that too much. Although maybe there is time, I'm not sure. Yeah, let's ask about it. So you did a little bit of density functional theory. Um, we're just asking about everything you've done in your life. It's just like a throwback day for you.
That's great.
Yeah,
Bringing
so-
back good memories.
So you did some dipolar Fermi gases instead of dipolar boson gases.
Yeah.
So what kind of stuff? So I don't know how much we've talked about density functional theory before. Probably not
Yes.
too much.
I mean, so I don't know. The lowdown of density functional theory is that it's kind of a cheap way of treating fermionic systems rather than boson. So bosonic systems, we talked about the Gross-Pitevsky equation, which is treating the bosons all as collective, in a very with one function as a collective object. Density functional theory is the kind of equivalent for fermions, but it's a little more complicated because fermions don't like to. Well, they behave differently, let's say, and it's not so easy to write down a very simple differential equation that describes their motion. But these systems, so as it turns out, it's been known for a long time that if you throw a bunch of electrons in a system like a 2D electron gas, they'll at some point they'll form a crystal. It's called a Wigner crystal, and it's been known for ages. I don't know how long it's been known for, but it's interesting. But the electrons have a 1/r, the Coulomb interaction. What we were looking at was the 1/r cubed, the dipolar interaction, and it wasn't really known necessarily whether it would form this Wigner crystal or whether it would form a sort of stripe phase or what it would do. And so this is what we were looking at with this other method, density functional theory.
Interesting. I know so me and Feely worked for Brandon a little bit as well, and I was supposed to do my undergraduate honors with him, but didn't end up doing it with him. I was supposed
Same.
to.
I was to do some airy gas stuff or something. Yeah.
Yeah, I was supposed to be basically working on developing a density functional theory for an anisotropic Fermi gas, which is something that at the time, I guess no one had done. Maybe they've done it by now, but so it's interesting that I don't know. We kind of took the same path by accident. I ended up working for the same guy, and then I swapped to Peter Marsland doing some other things, but I ended up finding Duncan by accident. I remember it was funny because I emailed Duncan because what I did for my PhD is I just Googled a bunch of profs and looked at like their papers, and I said, "Oh, these are interesting." So I emailed a bunch of them, and a few of them responded. And I came down and did a tour, and I remember I was in like Duncan's office or something. He's like, "Oh, like by the way, one of my students went to X," and I was like, "Wait, what?" So it was just kind of an accident. It's probably why he hired me, honestly. Probably.
It's maybe Canada just such a small world because when I first got to Queens, I didn't know anyone, right? Well, I didn't know anyone in the physics. And then I got to the office and Thomas Fowler was there. I was like, well. So I ended up working in the same office. We were in different groups, but I was just in the office, class side there because I'm the first student of my supervisor there. And we didn't have a lab group. Or like a lab assigned to us. So I got put into this group with Thomas and all these wonderful people, and it was great. So
All right.
gonna move
The
now
last
to-
question, and then
yeah, the last question So I think this one we didn't go too deep into childhood, but that's kind of good. So the one questions that I always ask, or not me, but we always ask our guests is the hope and dreams, because we want to know what are your hopes and dreams. What do you see yourself becoming? Who do you see yourself becoming? I'm not talking about like 5 or 10 years, but it holistically. Who are you becoming? Like, are you gonna want to be a scientist, or you want to be more like a professor, teacher, or maybe you want to be more, I don't know, half musician, half physicist? Like, what are your hopes and dreams?
Oh man.
It's a loaded question.
Yeah. This is a question I ask myself all the time. I guess it's important to ask yourself a lot. I think it's related to your plans in the future. Okay, like I think I've realized that I don't I don't want to say have a large. If I was going to become a professor, I would want to have a large group necessarily. I like the idea of having a small research group. I say I would I would like to be a professor if that's a path that's open to me. One of the things I don't like necessarily the path that ends up coming along with it. So I think a lot of these big groups, especially, you see the profs doing less and less and less science and being less and less involved. And basically, a lot of them end up just being there for like writing grants and sitting on committees and all this. And that doesn't appeal to me, which is a shame. It's a shame to me that the peak of your research career is almost like where I'm at now. and then
because you become somewhat a manager, right?
yeah,
Like,
and maybe when I get there,
yeah.
I would like it more. I don't know. Is the answer to that? So we'll see. But the bigger the group, I see often the less and less prof becomes involved, which is not something I particularly like looking forward to. But yeah, I would definitely say that a prof is a direction I would go.
I feel like Michael Berry is a good example of someone who just kept doing research. He never really had these massive groups. Most of his papers, it's just him and maybe like a second person.
Yeah, if I could be Michael Berry, then
yeah.
Well, that's a pretty good deal, like. Oh.
Yeah, I mean, like, look, okay, Duncan, for example, he's generally pretty involved. I think he almost has too many students for himself. I think
I agree.
Is quite busy, especially he's got kids, he's got all this stuff, right? Like these things take time. So, but yeah, it's difficult to say. If I found a job that would give me, I don't want to do something with my life where I'm just going to work and then I just turn off for the day. That kind of sucks. So holistically, let's say professor or researcher somehow would be nice, but I don't have a good answer for if that means
Yeah, I think sometimes, we don't know what opportunity is gonna fly by, and I think some of them only come once in a lifetime, right? And I feel like not taking those sometimes, like, ooh, if you're, let's say, like you're asked to work in like a very prestigious institute, for example, right? Like, well, maybe sometimes like, oh, do I really want to do that? Maybe I have a picture in my head what I want my life to look like, but well, if you have the opportunity, maybe I would take it, like even though it's not like the ideal thing, but I would do it, right? It depends on what comes our way, I guess.
Yeah, and sorry, can I just jump on that real quick? I forgot to mention this before, and that's this what you just said reminded me of this. My current job with Lorian and Thomas, there was no job posting, there was no anything. Like it was just basically my job with Russell was ending because he's a new prof and he didn't have the funding necessarily to keep me going. So I had to go somewhere else, and I just emailed out of the blue. I was like, "Hey, Lorian, I heard you're building a lab. Do you need a theorist?" And I was expecting the answer to be no, but then she was like, "Actually, you know what? Thomas is a guy who works in theory, and we're thinking of collaboration. So why don't you come over?" And so, yeah, I did that. So exactly, like this opportunity came out of nowhere, so I wasn't expecting it before I sent the email, so these things can just pop up.
That's kind of my goal, is to be a theorist for a lab, and seeing someone actually achieve that goal, who kind of followed a pretty similar path to me, is nice. Although I need to up my simulation skills a bit, but yeah.
Yeah,
Well,
I think
yeah.
it's cool. It was the first time I really all my simulations are in nanometers now, and I never used to think about actual units, and now I think about them all the time, right? So
Yeah. Well, thank you very much for joining us, Wyatt. For the sake of time, we're gonna move on and get ready to end the episode. But it was great to have you, and it's great to talk to you, and it's some really interesting stuff. So we're gonna end the episode with a story. But before we do that, we're gonna get Patrick to tell people how they can reach us and potentially reach you if you're interested.
Yes. So thank you, Wyatt, for joining us today. We are very excited to have you. And if you're listening to this podcast and you would like to be a guest on our show and talk about your field of interest, whether it be theory or simulation or experiments or field related things, we would love to have you on the show. So there are a couple different ways that you can reach us. The first is our email. You can send an email to hyperthesispodcast@gmail.com. We check that pretty often. So you can also send questions or comments about the episode, and you can also send us questions and then we can forward them to Wyatt. But if you want to contact Wyatt directly, what's the best way to do that if you do want people to contact you?
probably the best way is, email's fine. I don't know. You can put a link to my. Can you put a link to my website or something somewhere?
Yep.
That's
Absolutely, yeah.
that's fine. It also has my email address on there. Yeah,
Okay.
I'm also
So-
just look me up. Just Google my name and you'll find me somehow.
Yeah. So if you'd like to get into contact with Wyatt, his name is Wyatt Kirkby, and you can find his website in the notes below for this episode. And again, you can reach out to us as well, either through email or you can reach us on Instagram. We are at the Hyperthesis, where we're posting updates. So we're recording this one a little bit early before we release it. And so keep an eye on that when you do, because we're starting a new season, so we'll be posting a lot more. We also have a YouTube page, so you can like, follow, subscribe us. The animations are very cool, and they change every season. So make sure to check out the new ones for season 6 once it gets uploaded, and you can check out our back catalog there as well. We are found on pretty much any podcasting service available, whether it be Spotify, which we're based out of, along with Apple Podcasts, Google Podcasts, Audible, whatever you're listening to. Give us a rating, a like, a subscribe, a share, whatever you need to do, and wherever you're listening. And again, if you have questions for Wyatt, either reach out to us or reach out to him. I was looking at his website. It's well done. It looks nice. It's very descriptive, so you can find him on there.
Got some nice caustic photos floating around. We love them. Thank you, Patrick. Thank you for that, and thanks again, Wyatt. So today's story is also going to be Patrick telling it. It's going to be about a very well-known physicist named Paul Dirac.
Yes. So I'll try and make this quick. But the life of Dirac is very in-depth, and his work is phenomenal and still felt to this day. And it's something that we've mentioned many times before on this podcast, whether directly saying his name Dirac or just talking about the work that he's done. But he's truly one of the fathers, if not like the main father, debatably, of quantum mechanics. And not only was he important in the field, he coined important terms like quantum electrodynamics, and was also involved in several interesting projects relating to physics, but may or may not have had to do with the atomic bomb. And no, not that one. But this is a brief look into the life of Paul Adrian Maurice Dirac. So Dirac was born in Bristol, England on the 8th of August, 1902, to Charles and Florence Dirac. Fun fact, his mother was actually named after Florence Nightingale, and his father was a Swiss immigrant who immigrated to England and worked as a French teacher. Dirac's mother was Cornish, which at that time was a very important distinction from being English, and she worked as a librarian. So Dirac grew up in a fairly well-educated household, and he was very fortunate in that the schools that he attended were adjacent to the University of Bristol. Now, it's interesting that Dirac had a younger sister and an older brother, and they were all actually Swiss when they were born, and they weren't actually naturalized as English until after World War I in 1919. Now, as I said, Dirac attended a secondary school that was adjacent to the University of Bristol, and it was very unique in that it taught technical subjects like metalwork or modern languages, bricklaying, very technical fields that were not a very popular concept to teach at the time. A lot of other schools tended to focus on the classics. Now, once finished his secondary school, where he excelled in mathematics, Dirac studied electrical engineering at the University of Bristol. So there's that an engineer becoming a physicist and mathematician that we mentioned earlier. Now, he was able to finish his electrical engineering degree with first-class honors as a Bachelor of Science, and he was actually admitted right before finishing to St. John's College at Cambridge. However, he was unable to afford living in Cambridge and the tuition that came with that position, so instead he took up a Bachelor of Arts in Maths at the University of Bristol, which was free of charge. Now, he was able to skip his first year because of having a whole previous degree, and he fell in with Peter Fraser, who was his favorite maths teacher. It was him who inspired Dirac to look at projective geometry and applying those ideas to this kind of newfangled Minkowski's relativity. And you've definitely heard the name Minkowski on this podcast before. Now, he was able to complete this Bachelor of Arts in Maths with another first-class honors in 1923 and was awarded enough money, which was about £240 at the time, to live and attend school in Cambridge. And so he went to St. John's College, where he was able to pursue his interests during a PhD in general relativity and this emerging field of quantum physics. His supervisor was Ralph Fowler, and he was able to complete his PhD in 1926 with the first thesis ever submitted anywhere in the world on quantum mechanics. He then went on to Copenhagen and Göttingen before becoming a visiting professor at the University of Wisconsin-Madison. So he, from an early age, had ties with America, but his work was quite phenomenal and quite revolutionary, given that it was indeed the first thesis ever published in quantum mechanics. Just a quick note about his personal life. More than 10 years after finishing his PhD, Dirac married the sister of Eugene Wigner, whose name was Margit, also known as Mansi. They first met at a restaurant when she was visiting her brother from Hungary and saw, to quote her, a lonely-looking man at the next table. Now, Mansi married him later on in 1936 or 37, and she actually had children from a previous marriage who Paul Dirac raised them as his own. And she's really attributed to a part of his success because she allowed him to focus on his work while she took care of everything else, which is a little bit controversial nowadays, but it's good to have someone supporting you in life. Yeah. Now, returning to Dirac's work, he established some of the first and most important general theories of quantum mechanics, and in particular, the relativistic equation for the electron. He was also the first to develop quantum field theory, and as mentioned earlier, he coined the term quantum electrodynamics. He also coined the term fermion and boson, and a funny story about that is Dirac was actually quite modest. He didn't like having things named after him, and he lived in a time in which things were being named after him by other people. But when giving lectures, for example, when presenting the Fermi-Dirac statistics, he would just say that they were Fermi statistics. Also in those lectures, he would say that Bose-Einstein statistics were just Bose statistics, as he said, for symmetry. He was motivated by mathematical beauty and symmetry, and this definitely extended into other parts of his life, like having a symmetry in the naming of these different views and theories. Now, I wouldn't delve deeply into all of Dirac's work. It's extremely extensive. We could spend several episodes talking about it, and we have talked about his work in the past. I will list some of the things he's known for, and you can kind of count on your fingers how many you've heard of if you have taken an interest in physics or if you've studied physics. So these include the Dirac delta function, Dirac algebra, the Dirac operator, Dirac brackets, which were inspired by Poisson brackets, the magnetic monopole. He did a lot of work with that. The Dirac equation, and he also even worked to quantize gravity and had kind of the starting foundations for string theory with his Dirac membrane. He would probably cringe at the amount of things that are named after him and just say, oh yeah, it's a delta function, a Dirac delta function. But truly, his work goes on and on and on in the field of quantum mechanics and more. Now, much of his work was done at the University of Cambridge as a Lucasian professor of mathematics, where he worked from 1932 until 1969. Now, during World War II, during his tenure at Cambridge, he was actually working on what was known as the Tube Alloys Project, which was Britain's version of the Manhattan Project, where they were working to develop the atomic bomb. His work there mainly looked at the theory of using a gas centrifuge for uranium enrichment, and his work on that is said to be some of the best work ever on centrifuges and enrichment. Now, of course, Britain didn't develop the atomic bomb by the end of World War II. That was done by the Americans, but he was still involved in that project because he was a great and brilliant theorist. Now, Dirac moved closer to his daughter as he started getting older, and he actually went to move to Florida after 1969, where he spent the rest of his life and his career at the University of Miami and Florida State University in Tallahassee. So he stayed there from 1972 until his death in 1984, and he published over 60 papers in those final 12 years. And he said he was happy there, except for the heat.
I didn't know Dirac was a Florida man.
Yep, Dirac was a Florida man, and he liked it there. Except for the heat. He didn't like the heat. Now, earlier in his life, something that I forgot to mention that's a little bit important is the fact that in 1933, at the age of 31 years old, he won the Nobel Prize with Erwin Schrödinger for the discovery, quote, of new productive forms of atomic theory. He has many, many other honors throughout his life and continues to be honored today in the form of different awards and plaques. And it's interesting because he even declined his knighthood because he didn't want to be referred to by his first name. So he didn't want to be Sir Paul, he wanted to be known as Dirac. Now, he died at the age of 82 in Tallahassee on October 20th, 1984. Now, Dirac has left behind an enormous legacy in many areas of physics, not just quantum mechanics, but in relativity. And I mean, if you're studying physics, chances are he's touched it in some way. And I'm sure he would be modest about his impact and contribution to the field. He was known for being precise and taciturn. So I want to leave you with two things from him. And one is that he actually has a unit named after him, known as the Dirac. And this comes from who he was as a person, but one Dirac is defined as one word per hour. So he was a man of few words, and to exemplify that and to really hone that in, one time he was giving a lecture, and after the presentation, a colleague who didn't understand an equation on the board just said, "Hey, I don't understand that equation in the top corner on the blackboard." After quite a lengthy silence, the moderator said, "Well, are you going to answer the question to Dirac?" And Dirac replied, "That was not a question. It was a comment." So, very interesting man, very modest man, and a great legacy.
If I may add something, it just reminded me of there's a quote by Hawking. It says, "Dirac has done more than anyone in this century, with the exception of Einstein, to advance physics and change our picture of the universe."
There you go. Thank you very much for that, Patrick. And thanks again, Wyatt, for joining us. It was awesome to have you, and I had a lot of fun talking about this stuff.
Yeah, thank you, Wyatt. All right, take care, everybody.
Yes,
I'll
thanks.
talk to you
Thanks
guys
for having
next
me.
time.
Yes, thanks everyone for tuning in, and we'll see you in the next episode. Bye.
Bye, everyone.